Share screen.
I don't forget to, yeah, record, yes.
Yes. And I got a new notebook. I figured out how to do that. So
One page big.
it's, yeah, and then so I can fill that one up to 100 pages and then go on. I just didn't want to have to do that during class.
Movie night was class.
Movie night was good. Ben, you picked a good movie. Pre-lectures due, no homework due this week. Homework 3 will be due next week. Project 2 is due the following week. Then we have the midterm exam review, and the midterm exam is Tuesday, March 9th. If you want to take it online by Zoom, send me an email and I'll arrange a time for you to do that. I'm going to try to get everybody in probably Wednesday, March 8th, who's doing it by Zoom. Or I don't know what I'm going to do. I'll figure that out when it happens. Send me an email if you want to take it online, and we can set up a time where you can do that. Otherwise, it's in person. The default is it's in person. No, our class is, yeah, I don't know. It's not, not Monday, maybe Wednesday. Okay, we'll figure it out. We'll figure this out. Or it may be the same day, just a different time. I can't do that. There's only so much multitasking I can do. I've limited in that capacity. I cannot watch people on taking an exam by Zoom and have people taking it in class. So Tuesday, March 16th, I'm calling it pseudo spring break. It was in my schedule for called spring break. And then the university had apparently canceled it without consulting me. So there's nothing due that entire week because there's nothing due on the schedule. It'll give you a chance to kind of catch up on all your projects and things like that. Class will meet, and that will help me keep me from being so terribly far behind. We could watch a movie.
Bill and Ted is almost the exact same length as the class.
History of the World Part 1.
Yes.
The movie was great. It was perfect. It was kind of lighthearted and stupid, and a lot of puns in it, and it was enjoyable. So maybe you'll be around for the next one or resume workshop. Okay. I was so excited this morning. The standard bearer, the person who would, we had a real graduation, would be holding the sign that marches in as the college comes in. It's usually the outstanding senior from the college. That means engineering, informatics, and applied sciences. It's for the second time ever the standard bearer is a double E.
Oh.
And guess who it is? Corey Klein.
Hey.
Well, no, Corey's here this semester.
No,
he just,
he's gonna be back in person, or?
I don't know. But I don't think we're having a real graduation anyways. But he's going to hold the sign at the Zoom meeting.
You nominated?
Of course. Guess who nominated the first double E ever?
Wow.
No, that was me also.
Who was the first name?
Jack Gerard.
Oh, of course, Jack.
Okay. So I'm happy for him.
Yeah, I might have won for Corey.
I sent the email back. I had to hit reply all, kind of on purpose. It went to the dean, and it went to Ben, and it went to Kyle. I said, "Congratulations, Corey. I wouldn't have made it through last semester without you." The rest of them I could have lived without. I could not have gotten through last semester without Corey and Sean. They had my back, my assistant teachers. Voltage converters, and I've known Corey since he was a freshman. He's been a great student all along. He's been really helpful to the other students in the program too. He's a good guy. Yeah, he helps everybody. Okay, we want to talk about voltage converters today. Oh, there's another thing totally unrelated to class, and I'm recording. There are 2 people who are finalists to be the new NAU president.
Ooh, I saw.
One of them is an IEEE member.
Ooh.
Which one was that? Because I looked at both.
I don't remember. I have to go back and look. I think he was not the guy from Georgia Southern. He was not the zoologist. He was the other one. But there's an actual possible engineer going to be the president of the university. So we need to have a letter writing campaign to ABOR.
No, let's do it.
We could do something like that.
Do a little IEEE meeting where we just sit down and
where we honor the new president-elect. We could have our own convention where we nominate them. I don't know. Okay. Anything's better than an accountant. Sorry.
Yes. Yes.
My dad did not like accountants. Well, he was the he was the head of operations, and the accountants would give him this weekly, give him a binder this thick, full of data on what the mill was doing, and it always came down to the same thing because they were accountants. Look, this is great. Look how much money the mill is losing. And my dad was like, no, this is horrible. You cannot send this out to the people who work in the mill. It will destroy morale. All I want to know is I want one piece of paper, and on that piece, don't throw this report away. On this piece of paper, how many tons of pulp did we make? What was the price per ton of pulp? What were our labor costs? What were our operating costs? And I want it to be a positive number when we get done. That's the goal. Because people in the mill get raises based upon them making money, not based upon them losing money. That's why it's a bad thing when you tell people they're losing money every week. Okay, and one piece of paper, no binders.
Okay, so
They hated him for that.
was Corey getting nominated? Doesn't you were excited about?
No, he hasn't been nominated. He has been chosen.
Chosen. Is that what you were excited about?
No.
Okay. So very curious.
It's a whole nother thing, and it's getting messier by the minute. As always. Okay, so we're going to talk about voltage converters. Now, this is really important, and I didn't realize people didn't understand this until some of the grad students messed some stuff up very badly in the lab. Inside of, normally when we build a power supply, you usually think of it as I just pull the 5 volts off of there and it's magic and it comes to me. No, it's not really like that. You have, at some point, have to plug into the wall. It has to go through a transformer or some kind of converter, convert to DC. And you do that with a device called a voltage regulator. It could be a linear regulator, it could be a switching regulator, but this is the magic device that takes AC from the wall and voltage regulator, I'm thinking reference, and turns it into a very solid 5 volts reference to a very solid ground. Okay, you start hooking things up to this. What happens is the devices you hook up to this, thing 1 and thing 2, doesn't matter what they are. They could be ICs, they could be whole boards or anything like that, are going to generate huge amounts of switching noise. I'm going to use the term noise loosely, as electrical engineers do. They generate a whole bunch of garbage that ends up back on this supply. The garbage that thing 1 produces ends up on thing 2. Your first line of defense for this is bypass caps. This is the magic that makes your board work, is with every device, whether it's a circuit, an amplifier, an entire integrated circuit, you put these capacitors between the power supply and ground right at the chip, and that prevents the noise from thing 1 into getting into the noise in thing 2. Sometimes you have really sensitive components, and these really sensitive components, this capacitor filtering is not good enough. So what you do is you have something like, you know, your IRA, you're trying to take a picture and keep the noise down to 35 electrons. So what you do is you give it its own voltage regulator, And this V regulator is still referenced to the same ground. All our grounds have got to be tied together at some point. They may be separated and tied together at a holy point ground. 490 in the fall, I do a whole day on grounding. But this may still be 5 volts, but it is a separate supply. And that way, the noise from thing 1 and thing 2 cannot get into my very sensitive thing 3. Reference to ground. It may be 5 volts. It may. You want to talk about that? One of the first things you want to check when you have a board is you want to check the power supply voltages on all your parts. Not all digital parts run on 3.3 volts. And if you run your 1.2 volt with a 3.3 volts power supply, smoke happens. And whole printed circuit boards have to go back and be redesigned. That's a true story. Ground loop, yeah, that's my whole grounding day in 490. It takes a whole day to explain ground to you guys. So this is thing 3. Sometimes I have something like an ADC converter. And all the values, the numbers that this ADC it produces on the output are based on the voltage input relative to a golden voltage we call VREF. If you really want accuracy here, you don't tie this into your power supplies. Your power supplies are good plus 5 volt sources, but this is plus 5 volts plus or minus maybe 50 millivolts. If my VREF is changing by 50 millivolts, my ADC output is going to be randomly changing by plus or minus 50 millivolts, no matter what, even if my input voltage doesn't change. So a reference voltage is different than a regulator. A reference voltage comes from a special chip. It's no longer called a regulator. It's another class. You look at you go to TI or Analog Devices or some reputable analog company. Maxim is a good one too. Linear, which got bought by Analog. And you look for a VREF circuit. This gives you a view, and it comes off of a power supply, a DC power supply, reference to ground. And you do need to tie, these are true stories, you do need to tie the ground to that chip or your VREF just doesn't work. The things I realize grad students don't know. Okay, so there's a really long story behind all that.
So when you were just trying to do it without time to do it ground.
Or the negative power supply. Because those pens were hard to connect to. Okay. Why doesn't my circuit work, Julie? Because it needs a power supply. Okay, so VREF, we need to tie it. It gets its power supply from someplace else, but it produces this golden voltage that instead of being like plus and minus 50 millivolts, it's more like plus and minus 50 microvolts. And you need something like this if you need 12, 16-bit resolution on your ADC, because this is the golden voltage that your ADC compares the input to produce its digital output. Okay, we're going to talk about voltage converters today. And I decided that the circuits aren't nearly as important as stuff like this. Grad students, they're like pump engineers, which is you guys too. Okay, you have to learn these things somehow. I've realized that. And you don't learn it in your standard engineering education. That's why I babble about this stuff. Other confusion I've seen through the years, if you think about VCC, that's the voltage power supply at the collector. VDD is the voltage power supply at the drain. Somewhere in the switch from bipolar TTL logic to CMOS logic Engineers got confused and could never keep the name straight. On your project, I don't care if you use VDD or VCC. I don't care if you use VDD2 or VCC2. I care if you switch from using VDD2 to VCC2.
Consistency.
You've got to use the same name all over the place. Otherwise, they will not connect. Okay. So power supplies are generally called VCC or VDD. I've seen CMOS circuit, straight CMOS circuits that use VCC all the time. It's just habit. We get stuck in our little rut, engineering ruts. VSS is ground, is roughly in modern day logic where we aren't using PMOS logic anymore, or that horrible plus 12 minus 5 volt logic, or plus 5 minus 12, whichever way that worked. This is generally just ground. Inside your project, if you call up the tri-state buffer from generic 13, it doesn't have power supply and ground hooked to it. The internal device actually goes to probably VDD, and I think it's BSS. So since those are called out as names on that schematic, on your top level schematic, and I usually put all the power supplies, all the voltage sources on my top level, you need something that just ties VDD to a DC source, we were talking about before class, and also ties VSS. Otherwise, it doesn't know which VSS you picked. What else? Okay, VBB is not the power supply at the base or the gate, whatever you would think we would use. Almost nobody puts the power supply at the gate. They put switching sources at the gate. VBB, from a micron point of view, and from most people's point of view, is the body tie of the NMOS transistors. Now, there's a really tricky reason we'll get to by the end of this class why we don't tie VBB to ground. It has to do with the body effect. Okay. And I will explain why the other side of that capacitor is tied to VCC2 and not to ground. It's a magic trick. We'll get to that. So the voltage levels going into the chip, we have these right here, VSSQ, VDDQ. They're separate power supplies, just like dividing up those two 5-volt regulators I did on the last slide, is I want to divide VDD from VSS. They both may be at 1.2 volts, but VDDQ is the power supply I give to the crazy board designers that they can put all the noise onto that they want to. This VDD and VSS is for internal circuitry that I am going to very rigidly control to make sure they're good, solid 1.2 volts and ground, and that I'm not putting too much noise on them. So I have a separate power supply to drive the pins. And this is for the pins, the output buffer power supply. This is what I'm giving to the outside world. And they can mess it up if they want to, but they can't mess up the inside of my chip. VSS and VSQ are usually both set to 0 volts. VDD and VDDQ, they can be 3.3 volts, they can be 1.8 volts, 1.2 volts, 0.8 volts, whatever it is I've decided for that chip. I have internal voltages. So off of this VDD, because the only power supply I have coming into this chip that's internal is VDD and ground, VSS. Inside of there, I've got to take that single power supply and I have to create another power supply at VCCP, which is a higher voltage than VDD. So I'm going to need a charge pump. I'm going to need to create VCC2. Do not use the slash in your Mentor Graphics file name. Do not use the slash anywhere in Mentor Graphics. So that's why we call it VCC2. I need to generate that one. I'm going to generate a different VCC2 called DVCC2. This one I'm only going to have sending to the cell plate, the 1T 1C capacitor. I create another voltage supply called VCC2. I got to give it another name, so that's why I call it DVCC. And this goes to the digit line bias, so this goes to the sense amps. And that's to keep the sense amps electrically isolated from those 1T, 1C caps, because we don't want crosstalk there. Those tiny little 1T, 1C capacitors, if they get a little bit of stray charge on there, it could potentially change their value. So we just give it another power supply. And then I create an entire power supply called VBB. It's less than 0 volts to perform my magic trick. And this is the voltage for the bodies on all the MOS transistors. It took me a while to figure this out, why this was like this. And it was like a eureka moment with Jack here, where he was laughing at me. We had a lot of those, but they were good. It was a good class. So we'll get to why VBB is the way it is. We're using regulators to stabilize the internal voltages, even if my external supply is changing. Even if somebody hooked up a square wave generator directly to VDDX, my internal voltages will remain stable. It's generally unregulated, or what I have coming out on the output. I want good, strong regulation because I can control what the voltages are inside the chips. And I'm using a linear voltage converter. There's 2 choices for regulator circuits. The first one is a linear regulator. They use a lot of power, but they give you a really good voltage, clean voltage. The second is a switching power supply. They're really easy to hook up. You can buy them in little tiny chips, or you can build one fairly easily using a charge. It's one of those cap switching circuits. Those, you have to switch the capacitors. So you have a significant amount of noise at whatever that switching frequency is. You know, like 10 millivolts. And that can really mess up your sensitive circuits. It is. What I did in the lab, I built this quick, dirty power supply. That's the thing I was grousing about earlier, where you have to hook up the negative supply to make it work.
And grad students were not.
It was hard to connect to that pad, but it's the negative power supply. It won't work without it. Gee, maybe that's the problem. I'm doing this all by email too, which makes it harder. Okay. I don't know if the sarcasm comes through or not.
Be sarcastic in text.
We need a sarcastic font. Okay, so anyways, where was I at? Okay, so it generated, oh, my quick and dirty power supply. I used a switching regulator, but I was using this to drive a plus and minus power supply on a rather sensitive circuit. So I took the output of the switching regulator and ran that into a linear regulator that had a really high efficiency linear regulator. It could only supply maybe like plus or minus 10 milliamps, but it was enough for the circuit that I wanted. And that's the one that has the pins that I'm ready to hook up to. The pens are literally blobs on the back of the package.
That is kind of a pain.
It is, but get somebody to professionally build it. It's a beautiful circuit. It's my favorite regulator right now. DVC2, the version of VCC2 I'm sending out to the digit line bias. I can use a simple modified CMOS inverter. When I tell you this when I tell you on the homework to use the simple one, I'll point it out later. And VCC2 is a cell, yeah. I need charge pumps to generate voltages that are below VSS and above VDD. And the two big ones here are VCCP for our word line voltages and VBB for our body tie. Why do we want the body tie to be less than ground? That will always give us a VBS on our transistors, which means the body effect is going to come into this somewhere. We'll get to that.
Would you have that? I guess that's kind of been almost the motto for a bunch of the previous classes. That just like, don't worry about the body effect for now.
Yeah, no, I in 380, it's worry about the body effect unless I tell you not to worry about the body effect. And here we're going to deliberately use the body effect.
Yeah.
Okay, so the trend throughout the years, VCC goes down as the processing size goes down, because we can actually, with these smaller processes, as the F shrinks, as our minimum feature size shrinks, we have lower threshold voltages, and our lower threshold voltages mean we can lower VCC. Why we care so much about lowering VCC? The power dissipated in a static CMOS circuit equals roughly the frequency in like gigahertz times the capacitive load we have to drive. We always want this to be bigger. Everybody wants this to be bigger. The capacitive load we don't have a lot of control over. We can limit the length of the word line. We can limit the length of the digit line. The biggest thing we have control over here, and ooh, it's squared, is VDD. So not lowering VDD from 4 to 3.3, we don't just get a linear drop in the power, we get a quadratic drop in the power. And this is the motivation to going to lower and lower power supplies. Yep. Right. If we can drop VDD, we can drop the power dissipation by a factor of that VDD squared. It's a big deal. And that's been going on since I was in grad school. Okay. Now, I had a few questions about this in terms of I don't understand what this means, and I just said I would get to it later, Ben, and now is the time. We've got this external supply. And this straight line here is my external supply. Now we want to see what happens to my internal regulated supply when my external supply is going up. Sometimes the board designer, okay, I can laugh in here. I can't laugh about this other place. Sometimes the board designer, instead of giving us our 1.8 volts that we want, gives us 1.2 volts. What happens here if our input power supply is too low, the internal power supply is going to be low also. Doesn't cause smoke, but causes speed problems. Okay, so as this power, and generally when a power supply starts to power up, you go from your battery being, or your thing being completely off. It doesn't instantly switch from 0 to 5 volts. It actually ramps up. It takes a while for that power supply to charge all the capacitors on the board. So with time, the power supply is going to ramp up. We don't generally want to operate in this region. Usually there's some kind of control that says inside your circuit that says when the power supply gets to this value here, this magic value here, I'm going to actually power up my device. The external supply may still be going up, maybe like going up and up and up beyond that. But even if the external supply is unstable, or it's changing with time, or it's just increasing, or it's at the wrong value, we want our internal supply to be relatively flat. We can't keep it perfectly flat in the operating region, because if we keep it perfectly flat, we can't do this.
But you can reduce the curves.
Yeah, we can make it nearly flat. So if this is 5 volts and this is 4 volts, the internal supply is still sitting there at 3.3 volts. That's a good thing.
Right, now my question was on burn-in region.
It was about, and it's what, why do we do this? Okay, so what happens here in region 3? Suddenly my PCB designer puts a 3.3 power supply on a 1.2 volt part. The internal supply, it goes up into the burn-in region. We actually want this to happen, but if it goes up too high, it could actually burn the chip up. Don't do that. This region, this burn-in region, is used for testing. What I want to do, and that will lead me to my next slide, is the failure rate versus time. There's this thing called infant mortality. A lot of chips fail before they even get powered up. Some of them fail on the first power up, and this is like exponentially going up here. Some of them are weak. They could make it through 3 or 4 power cycles and some limited testing before they break. You don't want those to get into products that go out to the consumer, because they mean as soon as they've made a call on their iPhone 4 times, it doesn't work anymore. People get upset over that. Yeah, that happens too. So what we want to do here is we want to get rid of all the ones that are going to fail early. And the way we do that is something called burn-in testing. It's also called accelerated lifetime testing for your QC people. But basically what I want to do is I want to power up every chip, and I want to stress it a little bit. I want to put too high of a voltage across it. And I want to run it continually for too long of a time. And I want to switch the clock a little too fast. And this actually causes a lot of chips to fail that would otherwise get into product, and then those can get thrown out. We want to get rid of all of these. And that's why we do burn-in. We purposely run the power supply voltage a little bit high, not like 3.3 to 1.2 high, but a little bit high, maybe a 3.3 volt part, you stress it to 4 volts or something like that, to get rid of the early failures. This is the stuff you send out to the customer.
Right, and that actually makes much more sense than how the book described it.
Yeah, and I've been through this. I've actually done, well, I haven't done it. I've watched other people do it.
Would this be in the department of those guys, the 5 guys that sit in the room trying to break stuff?
No, this is a much bigger department. This is like QC and the what Paul always called the ilities engineering, reliability, testability. There's a lot of ilities people out there too. So there are people who do this. They test every chip. Those would be test engineers in under the ilities. One of the things is what I've always found is any job I've had, they never give me enough work. So to keep me entertained.
Except for last semester.
Except for last semester, which I had no time to entertain myself. So what I do in my spare time, when I was working, was I would wander around and talk to people in like the ilities engineering, or I'd ask them what they were doing, and and so I learned a whole lot about what was actually going on. I'd find solder joints that were cracked, and I'd take them to the guy with the electron microscope and go, "Can you take a picture of this for me?" When I get bored, it's dangerous. I can make everybody else work. I didn't send out many annoying emails last semester. Uh, so this burn-in is performed by the manufacturer or the customer, and maybe like okay, so let's say I'm building a flash chip, and it's going to go in an SSD. Both the manufacturer of the flash chip and the person that is building the SSD are going to burn in both of their parts. So some things may get burned in twice. There's a thing called accelerated life cycle where they want to see how long these are going to last. They want to figure out what this time is. And the way they do that is they run the devices at higher temperatures because that tends to stress it lower than lower temperatures, and at higher voltages, and see how long they think this thing is going to last. If a SSD is spec'd to last 10 years, that doesn't mean they test it for 10 years. They test it in a smaller time window at a higher temperature and a higher voltage and at higher speeds to estimate when that thing is going to die. And that's called accelerated life testing. And that's an ability to reliability, along with manufacturability and all that good stuff. Right, okay, we talked about all that. So now this curve makes sense. I need to have this after I get out of the operating range. I want the internal power supply voltage to go up if I raise the external supply voltage, so I can actually do these burn-in tests.
Roughly going up at about the same rate as the initial power up rate. So.
Right, because down here, if your power supply is a little bit low, you want all the voltage going to the chip you possibly can.
But for the purpose of burn-in, wouldn't you want it to go up a little more steeply to test?
You want to be able to control this. This just has roughly the same slope.
Okay.
There is another way you can do this, and that is on the next slide.
Right, I see.
This is called the crash and burn in. Part of the problem is if I'm operating right about here, maybe I have my fluctuations on that power supply are dropping me back down here, and suddenly my power supply is oscillating. You can't operate in that region at all, so you would have to start up here. So you miss that point right above what your max operating region is.
That answers my question.
Okay.
Just drastically decreasing.
Yes, and that answers Ben's question. Okay, so and I added an arrow to this today, which shows that I actually read the slides today. We have the way you build a voltage regulator. Generally, I just buy these from the experts, linear, analog devices. They have magic analog engineers who figure this stuff out. But you have a voltage reference. It could be referenced off of like a Zener diode, a reverse bias PN junction. There's fancier references, there's band gap references, things like that. You've got something that produces a pretty rock steady voltage reference right here that doesn't change much. The problem with these generally are they won't handle a lot of power. So if you hook this voltage reference, oh, I've seen people do this too. If you hook a voltage reference chip into the power supply of another chip, you're going to have problems because this at most can maybe like handle like maybe a milliamp or 100 microamps or something like this. It's a good voltage, but only for a very small power range. So the next step is you run this into a power amplifier, and there's a feedback loop in there. So the power that you're getting out has to go into some kind of controller that tells the power stage either to ramp up the output power or scale back the output power to give me a good regulated voltage here. Never tie, never tie a voltage reference into a power supply. It's like, okay. People don't tell you these things. Where do you learn these things in school? Dr.
Trying them
and blowing them up. Yeah, Dr. Yaramasi's classes. And this is like the important stuff that they expect you to know when you first walk out. Do you learn them in Dr. Yomasi's classes? Okay.
I didn't learn a whole lot, Dr. Yamaguchi's
Okay.
class.
Okay. Well, this is maybe power people. Yeah. It's all the analog stuff that's missing from your education. Because they all think you're going to just go out and program FPGAs for a living. Or program. Oh, there's a lot of you who will end up programming for a living. I hate to tell you that. Some of you will learn to like it. I just refuse. Right. We want to figure out how to get a good voltage reference. This is in no way a course in voltage reference design, as you will learn by like the next 3 slides. I have, what the heck is, okay, the thing inside the rhombus is, what is it? The trapezoid, that's the right word. I used to teach geometry, I don't even know that. It's an op amp.
It is an op.
It's because it's labeled an op amp. First rule of engineering, look for the labels. It's labeled op amp.
Yeah, the trapezoid's an op amp. I wouldn't expect that resistor to just secretly be an op amp.
The resistor is an op amp. I'm going to tell you that next time. Okay, what's inside this trapezoid? The way you could tell if it wasn't labeled is I've got this little thingy right here. I've got this diff amp we learned about in 380. Every time you see that, think op amp. This is labeled plus, and this terminal's this terminal's labeled plus minus, and this one's labeled minus. We'll pretend like that minus doesn't exist.
Only plus.
Only plus. So what we have here is something that looks like this: plus, minus. My output is the one that's labeled Vref. And if we want to think about what's going on with this on the first order, from Vref to the minus output, ooh, we have a resistor that's labeled op amp.
That's the name.
Never. Okay. And then from the positive input to VCC, we have R1. Okay. What do we have here? We have a non-inverting op amp, DC. It's going to take whatever VCC is, multiply it by the gain 1 plus op amp over R1, and give us our output. I don't have to think about that part of the circuit anymore. This piece of the circuit right here is to pull up Vref to VCCX when I hit that burn-in, when I want to do get that burn-in slope. And then I've got some other things here that I can use to, I can blow some fuses, determine which one of these are on. If all of them were on, I could pull this to ground. If only some of them were on, I could pull it to a different voltage. So I get a little bit of tuning here. That's all that circuit does. Whatchamacallit, what do I want to say here? Where is the voltage reference coming from? It's ultimately mapped to whatever the value of VCCX is, because it's going to be VCCX times whatever the gain of that circuit is. If VCCX changes, my reference voltage changes. May or may not be a good plan. And remember, VCCX is my sloppy power supply. We talked about that. That's to get the burn-in part of the curve. Vref, we want Vref to go up when during a little bit. Well, Vref can stay.
Zoom
Okay.
in on that one part.
Yeah.
That was the most script.
Yeah, we want to keep Vref fairly steady. Ideally, we want to keep Vref fairly steady, even when VCC is going up. We don't want it to depend on VCC. That last circuit I showed you, I'm suspicious that it depends an awful lot on VCC. Okay, things you see when you're shopping for a voltage reference or a linear regulator. The voltage out of these chips varies greatly. If the resistance changes, any of those resistor values changes, as the mobility of the electrons change, and mobility changes with temperature, which means everything changes with temperature. Threshold voltage changes with temperature. You can't control that. Temperature effects happen. In the real world, you build it, you read these data sheets, you find these numbers, and you model them to figure out what it's going to be like at your high temperature and your low temperature, and then you test them. We literally had these ovens that you could wheel around on carts to take our phones and our circuits and cook them or freeze them and see, does it still work? Power plots versus temperature. It was a fun, almost waste of time. You'd spend a week doing this to get like one graph of data points. And during this week, you probably had to work 1 hour a day to do this. And so the rest of the time you're running around looking for cracked solder joints to take to
It sounds like almost like painful because
there were solder sculpture. There's a lot of self-learning. You know, if you had to do one of these more tedious jobs, I would like open up a book and learn something. You've got the internet now, and everyone has a computer. That makes it better. I'd go around and talk to people, find out what problems they were having. I would work on other stuff occasionally, but you know, that would be my prime responsibility for the week. And I would go find a cracked solder joint to take to the SCM guy, go talk to the utilities engineers, find out what problems they were having that maybe I could fix. You find stuff to do. You always have to find stuff to do. Yes. And it's really the way you kind of like move ahead in the company too, or you become more knowledgeable about what's going on, become more valuable, is by talking to other people and, you know, exchanging information and figuring out, you know, all of a sudden that if you can see ahead that, oh, if I fix this little thing here, then this other guy's not going to have a problem. So it's valuable.
It all falls into place.
Yeah. As the temperature changes, the reference voltage is going to change. And we could model that as a derivative, but nobody takes derivatives in the real world. It's the slope of the line of VREF versus temperature. If I could plot that, and the people who make these chips do plot this, and they found that the slope is fairly linear within the operating region of temperature, and you get so many millivolts per degree C. It's one of the first thing you want to check on your voltage reference or your regulator. You want this, ideally, it would be a small number, because then you'd have a very small change in the reference voltage as the temperature goes up. And remember, that's going to affect everything else in your circuit. Dr. Brower said that. I will argue with that. The ideal temperature coefficient is positive, and her sunshine statement for that is it compensates for increasing delay with increasing temperature. So even though the delay goes up, the voltage goes up, which causes your delay to go down. There's a problem with this. Julie's one of my fundamental laws of everything. When the temp coefficient is positive, what happens? Okay, the voltage goes up as the temperature goes up. If the voltage goes up, the power dissipation goes up by VDD squared. And if the power dissipation goes up, things get hotter, which causes the voltage to go up, which causes the temperature to go up, which causes the voltage to go up.
Oh,
This is this horrible thing known as thermal runaway, where you have circuits that will self-heat themselves out of existence.
I can see why Dr. Brower would say that
Yeah.
ideal temperature constant is positive, but I think that your statement is more reasonable.
Well, you got to watch out for both of those. When you have thermal considerations are a big deal. It's the reason why you put heat sinks on all your hot parts. Basically something that's really conductive. They sell this amazing stuff called Silpad that is thermally conductive, but it's not electrically conductive. And it's in the form of tape. And you just tape it down to you can tape it down to your circuit board, put it underneath your part, and it will allow your part to thermally conduct to the circuit board or to a large heat sink like your chassis without causing shock problems.
I wish I knew about that during the capstone.
Yes.
That would be really helpful for our gesture sensors that were perpetually overheating.
One of my friends he had like an audio amplifier, and it was this particular chip on it was notorious for overheating, and he found a YouTube video on how to fix it. It was basically he had to reflow the solder on the chip because it got hot enough it cracked the solder. And he's going through all this stuff, and at the end it told him, well, and when you get done with this, you want to heat sink this to the chassis. And it was like, how do I do this, Julie? And I just went to SparkFun or someplace like that, and I got a roll of thermal tape, stick this on the top, glue it to the chassis.
Yeah, like Sarah and I were all just looking at it, like, I see this.
Yeah, it's called the heat sink. There was, I don't want to talk about it.
Like our gesture sensors were getting so hot, we just couldn't figure out a way to actually adequately dissipate the heat.
Heat sinks.
Yeah.
If you want to know about heat sinks, come and talk to me. One of my students, oh, he was amazing. He was an electronics technician I'm like a mechanic. And he came back to school, and he ended up going to grad school. He was a mechanical engineering major. And I adored him the second that he pulled out his thermal grease from his pocket and said, here, do you need he just always carried thermal grease in his pocket because he was a mechanical engineer. He had that hands-on experience to know these things. A lot of you don't. You should get a job as a, yeah.
Don't want to hire me.
There's one kid who's in grad school now. He's got a lot more sense than most of them. He worked at Home Depot in the electronics department. And it was just a matter of him, getting used to seeing all the parts, and there's an old electrician guy there, and he talked to them, and I came in once and asked him an embarrassing question.
You learn through experience.
You learn through experience, and you learn from talking to people,
yeah.
Not just from books.
I've learned a lot from helping my dad
Okay.
and working in the garage.
Yeah. Okay, so that region 2 slope. We want the region 2 is where we're actually operating. We want the slope to be fairly flat. So this is an improved voltage reference. Again, this is analog black magic, and I don't expect you to learn all this. You can kind of look at the parts and understand it. This here is a current source. It's a current mirror, like from 188. I've got some pull-up transistors. These references are going to determine the impedance to ground. I've got an op-amp right here. This is the current source for the op-amp. And I've got an output stage, and I've got some pull-up on there. That's good enough reading for first peck, and then you kind of like figure out what's going on. It's not a circuit I expect you to memorize. Right. Now, different types of references. The first one I mentioned was called a Zener diode. You can use those, but they're not very good references. They have a lot of temperature effects associated with them. The voltage you get out is going to change with temperature, and the voltage you get out is going to change with how much current you're drawing. So not ideal. One of the best ones you can get is a band gap reference. And it's the voltage reference is tied to the band gap of silicon, which doesn't change with temperature and doesn't change with how much current you're drawing off of it. The drawback of this to get a band gap reference is you have to use PNP transistors. Now, if you're working at Micron or Intel or Microchip, they don't have, they're building their process using a standard CMOS process that generally doesn't make PNP transistors. So you got to kind of like specially kind of kludge them into the substrate and have a big area separated for your PNP transistors. I get the same volt for different sizes. I get the same voltage, so it doesn't depend upon the size. It depends upon the band gap. I can ratio the current output by ratioing the sizes of the transistors and just matching them to each other. One's 10 times the other. I can do that fairly well, pretty reliably. Temperature coefficient, almost 0. The problems, I have a really high current. So I need a big area of my chip cordoned off to be able to take the heating from this 10 to 20 microamps. They inject current into the substrate. That current has got to be pumped out of the substrate, be isolated from the rest of the chip, or it's going to wreak havoc on you. But it has no dependence on VCCX. You don't have to rely on the external supply. This is how I do it. Basically, I've got 2 transistors here. The gate, the base currents, the base is grounded on both of these. So it's going to be determined. I've got the VREF on the output. The relative size of the, okay, so I've got one of these with these resistor values, and the one that's 10 times bigger is going to have 10 times as much current. So I can use that, analyze the circuit, and come up with what VREF is. Okay. This would be something that I would look at. First thing I would do is throw it into multi-sim and figure out how it works. And then I would start changing it.
So, so to clarify again, so just make sure I heard you right.
Okay.
Slide. So the band gap frequency of cell doesn't change.
With temperature.
Yeah.
It depends upon the chemistry. It's pretty much, it's like those S&P orbitals as you move them closer together. There's some gap in the quantum energies in between there. It's not temperature dependent.
That's good to know that that silicon doesn't change
Yeah.
the temperature in that respect.
I don't think any materials change much with temperature.
No.
That's not a primary effect. Okay. It's the one thing that doesn't change with temperature.
Fair enough.
Everything else is temperature dependent. Okay. So for the power stage, we usually use an op amp with a big open loop gain, fast response, low offset. You can use feedback to cut down the open loop gain at the gain of a lot of stability. The feedback reduces the temperature and process sensitivity. Feedback is an amazing thing, and we should learn more about it, hopefully in controls class or in power electronics. Yeah, something like that. How much time do I have? Oh, I'm out of time. This is a power op amp. Yes, it looks like an op amp. I don't really talk much about that. Power stage, I'm basically putting 3 op amps in parallel. To get, this is driving my power supply, so I want to be careful with this. I want to get to the real thing. These are level translators, you can tell because the level goes up. It's labeled. They could be, this could be a 1.2, this could be 3.3 volt logic. And we change the voltages in stages in between there. I almost want to like save some of this. Yeah, I want to save some of this for Thursday because some of this is important.
Right.
Rather than rushing through it. 40 slides. Let's see how much of this. We need the voltage pumps to get VBB at the body of the transistor. We're going to use PMOS only for that, and to get VCCP, we're going to use that. Let's save this since I have pseudo spring break. Is your exams before pseudo spring break? I can.
Yeah, it is.
Okay, slide 28. Let's save this, and if I don't get to semiconductor physics before the midterm, I'll be fine. Let's cover this. Save some of this for tomorrow, because I want to talk about the secret of why we have BBB less than ground, why the body effect suddenly becomes a good thing. Hamad, are you here? Yes, you're here. Yes, he is.
Of course I'd be here.
So the only people are missing are the ones who are usually coming from China, Shujian, and Yu Hao.
Matt's no longer missing.
Matt is, we've accounted for Matt.
I mean, we haven't seen him, but
We know that he's alive in some capacity.
Yes,
I think.
which is more than we knew last week.
Yes.
did you get an email as well today, Julie, that like professors are encouraged to take 2 self-help, like self-help, what's it called? Not self-help, I don't know, because spring break is gone.
Yeah.
I can't remember what the word is. You have the email?
I haven't even checked my email yet today.
Okay,
Mental health days. This past week, our Senate passed a resolution that asks faculty to consider inserting mental health days into their course.
So.
well, that is pseudo spring break.
That's what I'm
So
thinking.
we should watch a movie.
Well, no, what I,
You could take that day off.
well, the biggest thing I'm doing during pseudo spring break is there's no homework assignments due, there's no pre-lecture assignments due, there's no projects due, and there are no labs for the entire week.
Yeah,
Yeah,
that almost sounds like something for us though, and not something for you.
yeah. But, and then I get, well, I have a whole mental health thing coming up.
I'm excited.
You're excited for me, are you? It means I can go to work in the lab 1 week earlier. That may not sound like as much fun as it is.
I know it's fun just because of the little things you told me of how much fun it is.
Well, it's just, it's a lot less stressful. It's a lot, you know, I don't have a whole bunch of people ask me to do things. I just have to worry about the one guy. Yes. And make sure everything, and yeah, and just make sure the pup engineers don't
Burn it down.
burn things up.
I still trouble.
Yes, you need to do that.
Saying it's mainly because it's just like, well, actually, if it's behind, yeah, most policy, we're not technically behind as long as we get 3 weeks. 3 weeks, as long as you've done homework 2, then you're not behind.
I didn't, but homework 2 is my first homework.
Yes, it was.
I'm gonna stop
As long
recording.
as you've done homework 2, then you're not technically behind.
You guys can leave.